Hi there, it's Mr. O'Reilly here, and this is the second video on the kinematics of a particle moving in a straight line. As always, you can find me on Twitter at O'Reilly Maths and also on YouTube at O'Reilly Maths as well. So, the objectives for this tutorial are to understand three more of the SUVAT equations, and then to use these equations to solve problems involving linear motion of a particle with constant acceleration. So from the video before, we had derived two of the SUVAT equations, namely the first one here, v is equal to u plus at, and then also the second one, s is equal to a half of u plus v times t. So those two we had derived in the first video. Now we're going to have a look at deriving the next three. So first of all, if we start with the first equation that we came across, which was v is equal to u plus at. And if we do some rearranging here to make t the subject, we can subtract u from both sides to give us v minus u equal to at. And then if we divide both sides by a, we end up with v minus u all over a is equal to t. So what we're now going to do is we're going to actually substitute this value of t. So we have t is equal to v minus u over a. We're going to sub this value here. Instead of t, we're going to sub this into our other SUVAT equation. Down here, this one here. So s is equal to a half of u plus v times t. So instead of t, we're going to put in this here. So what we're going to get is s is equal to a half of u plus v plus there. And that's all going to be multiplied by t at the end, but instead of t we're putting in this here, v minus u all over a. So I'm going to put that in instead of t. V minus u over a. So when we multiply this out, we multiply the u plus v gets multiplied by the v minus u. So what that will give us is u plus v times v minus u. That will end up giving us v squared minus u squared. And then that's all over a. But again, that's times by a half, so really it's all over 2a. So again, if we want to multiply both sides here now by 2a to get rid of the denominator, we end up with 2as equal to v squared minus u squared. And then finally we can add u squared to both sides and rearrange, which will give us, first of all, 2as plus u squared, and that's equal to v squared. And finally we'll write that with v squared as the subject. Give us v squared is equal to u squared plus 2 as. And now we have a third SUVAT equation after the first two from the first video. So that third one here is this one here. V squared is equal to u squared plus 2as. Right, so we've now got three of the equations. We have the first two, and we have the last one. So we now need to derive these two here, which are both ones for S, which is we know is displacement. So we are first of all going to start with our, this time we're going to start with our second equation. S is equal to half of u plus v times t. Okay, so I'm just going to write it actually as S is equal to u plus v over 2, which is the same thing as a half of u plus v. So u plus v over 2, and now that's all going to be times by t. So this equation here, the second one, S is equal to half of u plus v times t, can also be written as S is equal to u plus v over 2 times t. So now what we're going to do is replace the v, this v here, we're going to replace that with u plus at, which we know v is the same as from our first SUVAT equation. V is equal to u plus at. So we're going to replace this v up here with u plus at. So let's have a go at that. S is equal to u plus, so instead of v now we're going to put in u plus at. So u plus at. Remember that's all over 2. And it's all multiplied by t also. So let's keep going with that and see where it brings us. So we've got S is equal to, well, u plus u is 2u. And we still have that at. Again, that's all over 2. And again, that's multiplied by the time. So, going a bit further, well, we've got 2u over 2, so the 2's would cancel, that just leaves u. And then we've got at over 2, which is really just a half of at. So it's u plus a half. Plus a half of at. And again, this is all going to be times by t. So finally, when we multiply each term inside the bracket by t, we end up with u is equal, or sorry, S is equal to u t plus a half at multiplied by t is going to give us a half at squared. So a half at squared. And that equation there is our fourth SUVAT equation, which we have over here. S is equal to ut plus a half at squared. Okay, so we now have 4 of our SUVAT equations. 1, 2, 3, 4. And the last one we need to get is this one here. S is equal to Vt minus a half at squared. Okay. So this time we're going to start with, if we we start with v is u plus at, as we know, our first equation. So v is u plus at. And if we just do a bit of rearranging there to make u the subject, what we end up with is, by subtracting at from both sides, v minus at is equal to u. Okay, so v minus at is equal to u. Now what we're going to do is we're going to substitute this value for u. So instead of u, we've got v minus at. We're going to substitute that into the last equation that we just derived, this one here. S is equal to ut plus a half at squared. So we replace the u here with v minus at. So we'll start with S is equal to ut plus a half at squared. So S is equal to ut plus a half at squared. That's the equation we derived last. And now we're replacing the u here with v minus at. So what does that give us? S is equal to v minus at and that's all multiplied by t, and then plus a half at squared at the end, plus a half at squared. So if we expand the bracket there, we get S is equal to Vt minus At squared. We still have plus half At squared at the end. So finally, we've got Vt, then we have minus At squared plus a half At squared. So they're common like terms, At squared and At squared here. So minus a whole At squared plus a half At squared is minus a half At squared. So that simplifies down to S is equal to Vt minus a half At squared. And that's our final SUVAT equation. So now we've derived all 5 SUVAT equations, and now we're going to look at how we can use these last 3, which we derived in this tutorial, to solve some problems. So the first problem we have is a particle is moving in a straight line from A to B with constant acceleration 5 meters per second squared. The velocity of the particle at A is 3 meters per second in the direction AB. The velocity at B is 18 meters per second in the same direction. Find the distance from A to B. So I have the diagram over here given to me in this case. So I'm just going to fill in some of the values here. As always, we have our 5 SUVAT equations up here in the top left corner, so we're just going to be deciding which of them is best to use. And as always, we start off with SUVAT written out. We fill in what we know. So what have we got here? So we're asked to find the distance from A to B, so that's what we're trying to get. We know that u is the initial velocity, which is 3 meters per second at A. We've got 3. We know the velocity at B, or the final velocity, is 18 meters per second, given again in the question. And there's a constant acceleration A of 5 meters per second squared. So A is 5. So we were asked to find the distance. We have u, v, and a, and we're also missing t. So which equation then would be the best to use? Well, if we have u, v, and a, and we're looking for s, which one would we use? Well, if we look at this last one here, we have 3 out of the 4. We have u, we have v, and we have a. So v squared is equal to u squared plus 2as. We can use that then to find the s. So v squared is equal to u squared plus 2as. So let's put in what we know. Instead of v squared, we're going to put in 18 squared. Because v is 18. U is 3, so that's going to be 3 squared. Plus 2 times a, which we know is 5. And then it's all multiplied by s. So when we tidy that up, 18 squared is 324. That's equal to 3 squared is 9, plus 2 times 5s, which is 10s. So if we subtract 9 from both sides, we end up with 315 is equal to 10s. And then divide both sides by 10, which would give us s is equal to 31.5. And that's s is for displacement, so that's going to be in meters. And that's our answer. So moving on to the next question then. This time a car is traveling along a straight horizontal road with a constant acceleration of 0.75 meters per second squared. The car is traveling at 8 meters per second as it passes a pillar box. 12 seconds later the car passes a lamppost. And we're asked to find the distance between the pillar box and the lamppost and the speed with which the car passes the lamppost. So if you'd like to pause the video now and just draw your diagram. I'm going to show the diagram here. I have it ready. Right. So we have our diagram there, and this time we are asked to find the distance between the pillar box and the lamppost. So distance is displacement, which we're looking for. U we know is 8 meters per second. The car is traveling at 8 as it passes the pillar box, so that's going to be 8. Then it says 12 seconds later the car passes a lamppost, so the time is 12. It gives the acceleration is 0.75. And the second part of the question asks us for the speed at which it passes, the car passes the lamppost. So that's the final speed. So that's also what we're looking for. Okay, so we have 3 of the 5. 3 out of the 5 of S, U, V, A, and T. And the first thing we're going to do is look for S. Well, we have U, we have A, and we have T. So we look up at our equations and we see which of these has U, A, and T, and also S. UAT and also S would be this third one here. S is equal to UT plus a half AT squared. So that's the one we're going to use to find this distance. So S is equal to UT plus a half AT squared. So S is equal to, well, U is 8 and T is 12. So that's going to be 8 times 12 plus a half AT squared. Well, A is 0.75, and that's all going to be multiplied by 7, and that's all multiplied by T squared, and T is 12, so multiplied by 12 squared. And when we put all that into the calculator, we end up with S is equal to 150, and that's going to be in meters. S is 150 meters. Okay, so on to part 2. We're asked now to find the speed with which the car passes the lamppost. So the speed that it passes the lamppost would be v, the final velocity, which we're looking for down here. We have the other 4 now, we have all of them. So we want one of the SUVAT equations then, which has v in it, and we just need to find, well, the easiest one obviously would be v is equal to u plus at, because we have u, we have a, we have t, so we can just use that equation. We'll keep it as simple as possible. So v is equal to u plus at. So means that v is equal to 8 plus a times t, so 8 plus 0.75 multiplied by t, which is 12. And when we work that out, we end up with 17. So v is equal to 17, and that's going to be meters per second, or ms to the minus 1. So that's the answer to the second part, the speed which the car passes the lamppost. Okay, if you'd like to have a go at this question now yourself, just pause the video, draw your diagram, fill in what you know out of SUVAT, and try and pick the correct equation then to work out what you're asked to find. Okay, so a particle is moving in a straight horizontal line with constant deceleration 4 meters per second squared. At time t equals 0, the particle passes through a point O with speed 13 meters per second, traveling to a point A where OA is 20 meters. And we're asked to find the times when the particle passes through A. So notice there it says the times when the particle passes through A. The total time the particle is beyond A, and the time taken for the particle to return to O, to the point O. So, start by drawing a diagram. So I have this prepared here. We've got O, A over here, and we're starting at 13 meters per second. So we're just going to fill in now what we can down here for SUVAT. So we know that the distance is 20, because it tells us here OA is 20 meters. So we've got S is 20. We know that U is the point at, or the speed of the point O, which is 13. V is, we don't have V, we don't know the speed at the point A, so we don't know that. We know the acceleration. Well, if the deceleration is 4 meters per second squared, that means the acceleration is minus 4. Deceleration is negative acceleration. And then finally we're asked to find the time. So we want to know the times at when the particle passes through A. So we're looking for the time. So we're going to use the equation then. If we have S, U, and A, and we're looking for T, well, we're going to use this one. S, U, A, looking for T. So S, U, A, looking for T. We're going to be using this one here. S is equal to UT plus a half AT squared. So S equal to UT plus a half AT squared. So let's fill in what we can. We know that S is 20. U is 13. T we're looking for, so 13T. That's a half A. Now A is minus 4. And that's multiplied by T squared. So when we tidy that up, we end up with 20 is equal to 13T minus 2T squared. So we can rearrange this then to form a quadratic. We bring everything on the right side over to the left. We get 2T squared minus 13T plus the 20 is equal to 0. And then we can factorize this quadratic here, and we end up with 2T minus 5 multiplied by T minus 4. And we know that that's equal to 0. So that means then that the times, the two times that we get is T is equal to 2.5 or 4. So 2.5 or 4, and that's going to be seconds, because that's the time. Now we have two answers, because the acceleration is negative, because it's a deceleration, the particle passes through A, then changes direction and passes through it again. Because if it keeps decelerating, it's eventually going to reach a point where it stops and turns back. So that's why we have two times here for T. So T is equal to 2.5 seconds or 4 seconds. So just if we want to visualize that, it starts at O, goes to A, it's about 2.5 seconds here, Takes 2.5 seconds to reach it. Then it goes on for another little bit, and it's still decelerating, and eventually it comes back on itself. And after 4 seconds, it will be back here again at A on the return journey. Okay, so now we're asked to find the total time the particle is beyond A. So the total time the particle is beyond A. Well, as I said, if it takes 2.5 seconds to get to A from O, and then by the time it goes on another bit and comes back, and it's 4 seconds before it reaches A again, well then the total time it will be beyond A would simply be 4 minus 2.5, the difference between the two times. And that's simply 1.5 seconds. So that's the answer to the second part. The total time the particle is beyond A is 1.5 seconds. And then finally we're asked to find the time taken for the particle to return to O. So obviously if it's come back on A, it's going to keep going back until it returns to O as well. So how long will it take for the particle to return to O? So what have we got? Well, we've now got a new situation because we're trying to find out how long the particle takes to leave O and then come back, go out through A, past A, and then decelerate backwards, past A again, and then back to O. So we're trying to find out how long that's going to take. Well, what would the displacement be if it leaves O, goes out to A, passes A, decelerates, and comes back on A, and then back to here, back to O again. We have to think about some of our SUVATs here. The displacement then from O all the way out and back, its displacement is actually going to be 0 because it's not going to have, it will have gone all the way out and back, but its displacement will be 0. It's still going to be at the same point that it began the journey from. So actually our displacement is not going to be 20 this time, it's going to be 0. So you need to set up a whole new set of SUVATs for this, okay? So you start again. I've left this 20 in here just to highlight it because so many people use 20 again here when it's not. So you're trying to find out the time taken for the particle to return to O. So the initial velocity is still going to be 13. The final velocity we don't know. The deceleration is 4 meters per second, so the acceleration is -4, and the time is what we're looking for. So we have S, U, and A, and we're looking for T. So S, U, A, looking for T, that's going to be this equation here. S is equal to UT plus 1/2 AT squared. So we've got S is equal to UT plus 1/2 AT squared. So S is 0. The UT is 13T. Plus 1/2. A is -4. And T squared again. So when we tidy this up, we end up with 0 is equal to 13T plus 1/2 times -4, which is -2T squared. And as before, then we're going to set up a quadratic here again. If we bring everything over to the left side, we end up with 2T squared minus 13T is equal to 0. So 2t squared minus 13t is equal to 0. Well, we can factorize t out there. So we get t bracket 2t minus 13. That's equal to 0. So then we know that t is either equal to 0 or 2t minus 13 is 0, which means that t is equal to 13 over 2, or 6.5. And again, that's going to be in seconds. So that's going to be our two answers. Now it asked us for the time taken for the particle to return to the point to the point O. So t equals 0 would be the particle began at that point 0, that point O, when t was 0. So that's when it left, and the time it returned was 13 over 2 seconds. So really, that's the answer there. The second one is the answer to the question you were asked: the time taken for the particle to return to the point 0. Okay, and that's the end of kinematics, so you can just try some more questions yourselves.